Okay, so just a few comments to get going. So I've been sort of reading this mantra for some years now, but I think it's still relevant that optimization is being revolutionized by its interactions with machine learning and data science. I think that came through it in Wotau's invited presentation. First of all, it's given rise to a lot of new algorithms and a lot of new interest in old algorithms, like stochastic gradient is a classic example of that. Machine learning has thrown up a lot of challenging formulations and new paradigms, new kinds of problems that we want to solve. It's sort of cast different, it's shed or given new emphasis to certain topics, particularly for many years on renewed interest in convex optimization methods, issues of complexity, issues of non-smoothness showing up in objectives with certain kinds of structure, and various other topics. And there's now a very big research community that works at the interface of machine learning and optimization, and in fact along the whole spectrum. It's getting harder and harder to sort of distinguish the two communities. So, okay, so what's the purpose of data science or ML or AI? These are all, slightly different things, but two of the fundamental purposes of these areas are to extract meaning from data. You've typically got a large collection of data. You're trying to learn what are the important features in the data that you've got to pay attention to, and what are the fundamental structures. And the second thing you want to do is to go on from that and use this knowledge that you've learned to make predictions about other similar data. And then you could go even further than that and say, well, I want to use these predictions to take good actions, maybe optimal actions. And so that's where, optimization's traditional role as a decision science comes in as well. So I'm going to revert to this typical setup, which shows up in a lot of data science problems. The typical setup is after a whole lot of work cleaning and formatting data, ideally what you end up with is a set of M objects. And these objects have two pieces to them. One is a piece AJ, which I'll call a feature vector, and the other is YJ, which I'll call a label. Okay? Now the label can take many, many forms. It can be a real number, and then typically you've got a regression problem. It could be some kind of a label where you're trying to place the vector AJ into one of M classes, big M and YJ tells you which class that AJ is in. You can have situations where there are multiple labels, where you want to regress against multiple criteria. And you can also have a lot of interesting problems where there are no labels, where the YJ is null. And in that case, you want to somehow organize the AJs in some useful way. Like you might want to cluster the AJs into sets with presumably similar properties, or you might want to find subspaces that all of the AJs lie on. For example, AJ might be a very high-dimensional vector, but all of the AJs might lie on some low-dimensional subspace or manifold. Okay, so the classical perspective on data analysis is basically what you want to do is to learn a mapping that takes you from the AJs to the YJs by observing a whole lot of AJ-YJ pairs. So we'll call that mapping phi. And not only do you want to find that mapping, but you might also want it to satisfy a bunch of additional properties. So you might want it to be somehow plausible for the application that you're working in. You might want it to be somehow robust to perturbations in the AJs. You want it to be generalizable. So if you come along with another vector A that's similar to some of the AJs you've seen before, you want the map to behave in a predictable way. And you also want it to be consistent with prior knowledge. If you have prior knowledge about the mapping, you want to somehow be able to incorporate that into phi. So very often, this is reducible to a data fitting problem in optimization because you can parameterize the mapping phi in terms of a vector x, and the whole problem becomes trying to find what x is. And you can write that down by formulating a loss function, which tells you what's the difference between phi of AJ parameterized by x and YJ. You can take those two things and see how different they are, and if they're too different, you incur a loss, which is captured by that big L. And I'll be more specific about that momentarily. So very often the problem you want to solve is to find the x, the parameterization of phi, that minimizes this averaged loss over all of the samples that you're observing. Okay? Now in the case where there's no YJ, the phi could do something like assign AJ to a cluster or a subspace, and so the loss function could be defined that way if there's no YJ. So how do we use the phi? Once we've learnt the phi on a collection of training data, we can use it to make predictions. So I come along with a new data vector AK. I'll just plug that into phi, look at the output yk, and use that as the prediction of the label or the real number or whatever it is. I can also do some analysis. So just by looking at phi or the parameter x, it will reveal something about structure in the data. So for example, it might tell me what are the important components of the vector aj in determining the yj. And there are other sorts of structure you can see as well. For example, if your phi takes the form of a decision tree, then you can, by looking at the decision tree, you can build a lot of intuition about how to go from the aj to the yj. Now, in real life, there are many, many complicated problems that we're not going to talk too much about. One is that in real data, there's often noise or error in either the feature vector or the labels. Very often there's missing data, so some of the elements of aj may not be known. There's also this classical problem in statistics of overfitting, where the mapping phi does a fantastic job of correctly labeling the training data, but when you come along with a new piece of data that looks similar, it doesn't do so well. And this has been a well-known issue in statistics for many years, but something very interesting has happened in recent years in data science that overfitting has turned out not to be that big of a problem. You can get models, often neural network models, that exactly fit the training data and still generalize quite well. And understanding why that happens is a major area of study these days. Another issue is distributional shift, that when you're collecting the training data to determine what phi is, the distribution that the AJs are coming from might actually move during the collection process. And then when you come to actually use the phi to label new data, the distribution might have moved again. And so you'd ideally like the phi to be not so sensitive to those kinds of shifts. Okay, so a lot of optimization algorithms are used in solving this problem that I've outlined. And I like to sort of talk a little bit distinctively about formulations and algorithms. So formulations, optimization formulations are interesting in this context because they give you a way of translating statistical principles like risk, likelihood, significance, generalizability, and so on, distilling them into measures or functions or constraints that you can actually turn into a concrete problem that you can then attack with an algorithm. And then optimization algorithms give you a practical means to solve those formulations, okay? And to be efficient on these problems are often very challenging just because of their size. To be efficient, you need to really account for the structure and also the context. By context, I mean, do you really want a super accurate solution or are you happy with an approximate solution? That might influence the way you choose the algorithm. A couple of other things to pay attention to. One is that non-smoothness turns out to be interesting in a bunch of contexts, but it appears often in data science in sort of a highly structured way that algorithms can exploit. And non-convexity nowadays is widespread. People sort of ignored the issue of non-convexity for a long time, but eventually realized that, well, you can't really ignore it because, for example, neural networks are extremely non-convex. And so now when people are thinking about algorithms and analyzing them, they take account of non-convexity. And then duality is valuable in several situations as well, which I'll mention as I go. Machine learning is very influential in continuous optimization. It's sort of caused optimizers to become more interesting in issues of computational complexity. It's sort of shown them these problems where you actually prefer to get an approximate solution cheaply than to spend a lot of resources to get a super accurate solution. Another reason is that these are very huge, challenging problems. You really have to use parallel computing to find answers in a reasonable amount of time. Also, it's given renewed interest in methods that use approximations to function or gradient values, such as stochastic gradient, because exact functions and gradients are very hard to get. And also, it's given rise to renewed interest in certain classes of methods, which I'll come to as we go along. A couple of preliminaries. I'll be referring to this term convexity a lot. Here's a formal definition of convexity. Basically, if I was able to draw on the screen, I would, but I can't. But basically, convexity is when the function has sort of a bowl-shaped, okay? Another way to think of it is that if it's differentiable, the second derivatives are positive definite. Now, strongly convex is where there is actually a non-negative curvature. You don't have any flat regions in the function. That turns out to be a useful property. You get faster algorithms if they've got that property. Okay, so now I'm going to launch into this list of 16 problems in data science that are expressible as optimization problems. I'm going to start with the most basic one that dates back more than 200 years, linear least squares. And to put that in the language of what I've been talking about earlier with the function phi mapping the aj's to the yj's, phi here takes the form of aj transpose x, okay, where x is the weights that you apply to the different components of aj to predict yj. Now, you might think, well, I certainly thought this was a solved problem. There were books put out by SIAM in the 1980s and 90s about how to solve large-scale linear least squares. It's still a hot topic in machine learning. Papers show up in Europe's and ICML about large-scale linear least squares problems. And in fact, in industrial practice, this is used extremely widely, this very basic paradigm. Now, there's a couple of modifications of this that have been around for a long time. One is you can reduce the sensitivity of the solution to the noise in Y by doing Tikhonov regularization. That's where you add on a multiple of the square of X. And then more recently, since 1997, Tibshirani's paper, people have paid a lot of attention to this lasso formulation where you add on a 1 norm of X. And that tends to give you a solution X which has a lot of zeros in it, so relatively few non-zeros. And though the location of those non-zeros tell you which are the important components of the vectors aj. So that's application one. Application two is kind of extensions of this linear regression idea to beyond least squares modeling. So that if you suspect, for example, that the yj's have some outliers in them, if you've made some gross errors in reading the label yj, it might be useful to use a loss function other than least squares, because least squares places a lot of emphasis on large residuals. And so you can have a function L which sort of tapers off at a certain point, possibly even in a non-convex way. And also the regularization function, the R, I've showed you that you can use the 2 norm squared or the L1 norm. There are other norms as well that people use. Some of them are called SCAD or MCP, where they do have this property that they behave like L1 when X is close to 0, but they flatten out when the components of X get large. Okay, and this gives rise to non-convexity in many of these robust issues. Here's another application to matrix sensing or matrix completion. The problem here is that you've got a big matrix X, you don't know what it is, but you're able to probe it. You're able to take linear combinations of elements of X and get estimates for what those linear combinations are. So the AJs are these observations of X, these linear observations of X, and from those linear observations you hope to reconstruct what X is. So this is another kind of regression problem. In fact, it's kind of a special kind of least squares problem. But the twist here is that we have some additional information about X, namely that it's got low rank, okay? And then we don't need nearly as many observations to recover X as we would if it was a full rank matrix. So back in 2010, Recht, Fasel, and Perillo showed that you could use an analogy to the L1 norm for vectors X. The analogy in terms of matrices is this nuclear norm, which is the sum of singular values. So if you add on to this objective a nuclear norm term, it will recover a low rank solution and will also be a convex problem. So people did a lot of work using algorithms to sort of attack that formulation. You do need these so-called incoherence assumptions on the AJ or the X. Typically you can't be just evaluating single components or looking at single components of the matrix X unless you know that it's got some sort of incoherent form, namely that the eigenvectors are well spread out. They're not sort of focused on particular components. Otherwise it's like looking for a needle in a haystack. Now the disadvantage of this formulation involving the big X is that if you're solving a problem where M and N, where the dimensions of X are in the millions, this is an impossibly large problem. And so people got the idea of early on of saying, well, let's use an explicit formulation. Let's express X as the outer product of 2 long skinny matrices, L and R. The problem with this formulation is that its advantage is that you're hardwiring the low rank property into the solution. The problem is that it's a convex. It's now a non-convex problem. But nevertheless, people showed pretty early on that you could reliably find a global solution of this problem Typically solving non-convex problems is hard, but this one isn't so hard. And understanding that has been a major area of study. And I'll get back to that later on. Okay, non-negative matrix factorization. So this is a little bit of a twist on that low rank problem, where you know in addition that the two low rank factors, those two long skinny matrices, are also non-negative. They have all non-negative elements. This shows up a lot in applications, computer vision, document clustering, and so on. There are a whole lot of communities of people in these different application areas that have worked on algorithms for this over many years. Okay, and there might be other structures as well. For example, you might know that in the matrix L or in R, that the columns have disjoint support, that all the non-zeros in one column of L, those locations in the other columns are all zero. They can have that sort of property. That's very typical as well. Here's another one, which I think is very beautiful, is recovering dependency networks among collections of related random variables. So here, I'm thinking of the Z as being a random variable, a vector random variable with P components. And what I know is that those different random components of Z are related in different ways. They all have, they tend to move together or in opposite directions. And what we're trying to do is to recover the dependence relationships between the components of Z. And what we have to work with is a bunch of samples of Z. We're allowed to make independent draws of Z. Suppose we got n of those. So I can use those to form a sample covariance matrix in the classical way, given by this formula. And it turns out that the way that you can figure out which components of Z directly influence other components is by looking at the inverse of the covariance matrix. The locations of the non-zeros in the inverse tell you about the direct relationship between any two components of V, okay, of Z. So because you're looking for the most important relationships, you actually want to sparsify the inverse covariance. So not only do you want something that's approximately equal to the inverse of S, but you want a sparse approximation of the inverse of S. And you can write down, and this has been around since 2008, you can write down a little optimization problem involving an unknown X whose solution is a sparse approximation to the inverse of S. It's got this form, it's got a log det in it, it's got an L1 norm. L1 norm shows up a lot when you're trying to sparsify things. Here's a bit of a picture of what's going on. Here's a network. I've represented the 6 components of Z by these 6 nodes in a network, and the arcs represent the direct relationships where, for example, component 5 directly influences component 6. Now you can see here that components 4 and 6 in this picture will be correlated. There will be a correlation, but that correlation is 100% explained by the fact that they're both related to component 5, okay? And what we're trying to uncover here are the direct, conditionally independent correlations, and that's what this process does. So these arcs correspond to non-zero locations in this sparse inverse covariance, indicated by the stars there. Okay, sparse PCA, another very, very popular paradigm, and this has been around since this paper of Desperate-Moore and Jordan, and I think a couple of other people in 2007 that won a Best Paper Prize at the SIAM optimization meeting back then. So their goal was to take the sample covariance S and to find a sparse approximation to its leading eigenvalue, the eigenvalue corresponding to the biggest, eigenvector corresponding to the biggest eigenvalue. And they're able to write that down, or at least a relaxation of that problem, as a semi-definite program. So they use this matrix M, this n by n symmetric positive semi-definite matrix, as a proxy for VV transpose, where V is the sparse vector that they're looking for. And they put constraints on M. For example, they have the sparsity constraint involving the L1 to give you a better chance of finding a sparse vector M. And by squeezing the R down far enough, you end up with a rank 1 M. Choosing the R is a bit of an art form here. Okay? Now you can sort of extend that to the case where you want the leading R principal components, not just the first eigenvector, but the first R, by just changing that constraint that says that the trace of M has to be 1, you just change that to the trace of M being equal to R, and you end up with a sparse approximation to the first R singular values. Now you can do this again. Again, this formulation has the disadvantage that the unknown that you're working with, M, is an n by n matrix. So if n is in the tens of thousands, this is a big problem. But you can do this again using a explicit low-rank parameterization, just expressing the M as the outer product of a skinny matrix F with itself. Everything's symmetric here, so we just got FF transpose. And you can use this norm that's called a sort of a group regularizer norm. You can go down the rows of F, take the L2 norm of each row, and add those all up, and that gives you this norm F2, 1. And that's the thing you constrain. That promotes sparsity of the rows. It gives you sort of sparse approximations to those leading eigenvalues. And this is work due to my colleague Yudong Chen, who's now at Wisconsin, and Martin Wainwright, and several other people. Okay, number 7, robust PCA. So there are a lot of cool applications where you're making observations of a matrix Y that's actually the sum of two matrices. One of them is sparse, and one of them is low rank. So the M here is the low rank one, and the S is the sparse one. So you can write this down. If you're given the whole matrix Y, you can write this down as this problem of minimizing over M and S of the nuclear norm of M plus some multiple of the one norm of S, subject to Y being equal to M plus S. And of course, there are variants of this problem where you only know certain things about Y. You only have observations of Y. You don't know the whole matrix. This shows up, for example, in video processing. If you've got many frames of a video, the background is the same in pretty much all the frames, but interesting things happen occasionally in the foreground in a relatively small subset of the frames. So in this case, what's happening in the foreground is going to be the sparse part of the matrix. What's happening in the background is the low rank part, essentially. You can also write this by doing a compact formulation of M. You can express M explicitly again by using these two skinny matrices L and R. Okay, here's some work that I did with Laura Balzano, and she worked with other people on this as well, on doing subspace identification. So the problem here is you're given a lot of matrices, a lot of vectors AJ, and you want to show that they lie in a low-dimensional subspace. The trick here is that AJ are missing elements. So one of the cool examples for this is structure from motion, where you're trying to reconstruct a three-dimensional object from various two-dimensional views. And the twist is that this object is opaque. So when you see the surface of this object, you're only seeing the side that's facing the camera. So you're only getting an incomplete observation from each angle. But still, you want, from multiple observations, you want to be able to place all of these reference points in a three-dimensional space. Okay, so that turns out to be sort of an interesting least squares problem. The matrix X here is the matrix whose columns span the subspace that the A's mostly belong to. Okay, support vector machines. This was before neural nets came along and destroyed everything. SVM was the big game in town. And I'm going to show you some pictures which you've all seen at least 50 times before. The game here is that in the two-class problem, Yj is a label, +1, -1, and the AJs are vectors in n-dimensional space, and you're trying to find a separating hyperplane that neatly separates the two classes of AJs. So that hyperplane is going to be defined by a vector x that's in Rn and a scalar beta that's the intercept. So, and you want ideally to choose x and beta so that all of the +1 AJs lie on one side of the plane and all of the -1s on the other side. So in terms of that mapping that I described very early on in the talk, you can think of the phi as being just the sign of AJ transpose x minus beta. So what you can do is to write down an objective that sort of incurs a penalty when these conditions that I've written up here are not satisfied. Okay, when one of the AJs is either too close to the hyperplane or on the wrong side, this function down here is going to be positive. So we're going to incur a penalty for that. And by minimizing this function, by choosing the x and beta that minimize this function, we minimize the number or the amount of these violations. Okay? You can also add a regularization term to this function. That will tend to give you what's called a maximum margin classifier. So here is a picture that you've seen many times before. The two classes are illustrated here by red circles and blue squares. And the line I've indicated is a satisfactory separating hyperplane. It's not the best one, right? Because the two classes that I might be working with, the training examples that I've got, the AJs might just be observations of some true underlying classes that are given by these two big blobs. And obviously the hyperplane that I've chosen doesn't ideally separate those two classes. If I turn it around a little bit, it does. And so that's the function of adding on that regularization term. It tends to give you a hyperplane that's as far away as possible from all of the examples, like this one here. Now, of course, in practice, because of noise and so on, and nonlinearity, we don't typically get this very neat separation. We often get a little bit of mixing at the boundary. So the value of that function h at the solution might not be 0. It might still be strictly positive. So there was this wonderful invention that dates back now 30 years of kernel SVM, and the idea of this was that instead of restricting yourself to a linear separator between these two feature vectors, you first of all lift them up into a high dimensional space. So you take the components of AJ and you combine them in all sorts of interesting ways. You might take, products or squares or, polynomial functions or something, and you lift them into a higher dimensional space, and then you look for a linear classifier in the higher dimensional space. This gives you a much better shot at being able to neatly classify the two classes. You're giving yourself much better flexibility, okay? So you can write that down exactly the way that I wrote it a couple of slides ago, but instead of AJ, I've got psi of AJ, where psi is the lifting function. Now, the observation that was made way back in the 90s was that this is a convex quadratic program. At least if you introduce some extra variables, you can turn it into a convex QP. And you can take the dual of a convex QP, which is also a convex QP. And I've written it here in the middle of the slide, okay? And if you look at the Hessian of that dual, this matrix Q, what it consists of is the inner products. The KL element of Q consists of the inner products of psi of AK and psi of AL. And so you can write down the dual and you can solve it, and you can use the dual solution to recover a separating hyperplane without ever actually needing to know the psi explicitly. All you need to know are inner products of the psi's evaluated at two versions of A. And so you just have to work with these inner products, and you can introduce this thing called a kernel, which captures the inner products. So the kernel just takes two AJs as arguments and outputs the inner product of the psi's for those two AJs. So people tend to work with just the kernel. They never explicitly, it has been done that people explicitly write down psi's, but more often they just define a value for this kernel. And the one that's usually used is some sort of exponential of the difference, of the norm of the difference between the two A's, AK and AL. So kernel SVM was huge from the mid-90s through, I guess, 8 or 10 years ago. Okay, multi-class logistic regression. So this is, I've been talking a little bit about regression where we've got classification problems where we've got two classes. But what about, ImageNet, where you've got, order of 1,000 classes, where each AJ can belong to one of 1,000 classes. So one way of tackling those problems is that you try to recover these odds functions. So you come up with a set of odds functions called PL, where L goes from 1 to M. And if you plug a vector A into PL, AJ, it will give the odds of AJ belonging to class L, okay? And so you want the PLs, for any given A, you want the PLs to add up to 1. So the probabilities add up to 1, you want them all to be non-negative. So a very natural way to classify that is by this so-called softmax of a bunch of exponentials. So I parameterize the PLs by vectors XL, just like I did for linear SVM, but I take the exponents of A transpose XL in the numerator and denominator, and you can see that if I just sum these PLs up from 1 to n, given by that definition I'm going to get 1, you can see that they're also going to be non-negative. Now, how do I choose the XLs? That's the critical thing here. I want to choose the XLs so they do a good job of classification. So the idea is you want to choose all the XLs so that the correct class gives you a much bigger inner product with AJ than all of the incorrect classes. So if AJ has label YJ, where YJ is, goes from 1 up to M, you want AJ transpose X for the YJ to be much bigger than AJ transpose with all the other X's, because that will make the PL for that AJ close to 1 for the correct class and close to 0 for all the others. And so you want to write down an objective function that forces the X's to have this property. And it turns out this log exponential function does the trick. And it's also convex, which is kind of a bonus. If you expand it out, you see that it's convex. Non-linear, of course. Okay, so this is one way to do classification. Very often it's what happens at the last layer of a neural net. So you can think of a neural net, this is probably controversial to say this, but you can think of the neural net as taking a bunch of raw features, which are the components of AJ, and transforming them into some other feature vector by the time you get to the second last layer of the neural net. And then what happens in the last layer is you're essentially doing this. You're basically doing this multi-class classification on the output of the bulk of the neural net. We'll come back to neural nets in a moment. Okay. Here's another problem, community detection in graphs. This one's somewhat controversial because you can take graphs like friend relationships of people on Facebook, and you can sort of analyze them to find how what are the structure of the communities that they form. So the classic problem in this area is that you've got a situation where there are two communities, and the probability of being connected to someone in your community is a little bit higher than the probability of being connected to someone in a different community, in the other community. So that's very clearly illustrated in this graph, where there are two communities of size, I guess, 5 or 6 nodes each, and it's pretty clear how to divide them between the two. If I were to rearrange the nodes on the page, it wouldn't be so clear as it is here. So this is the canonical problem. Given that the within community connections are higher than without community, how can I write down a problem that will tell me what the two communities are? And that turns out, I had a lot of slides with details of this on, but it takes too long to explain. But you basically use statistical principles to come up with an objective. Okay, adversarial machine learning. Probably most of you know what that is by now. It's been around since about 2013. And it came from this observation that you can take a trained classifier, usually a neural net, and by doing a very small perturbation, but very well chosen, it can't be a random perturbation. You have to be very careful about how you choose it. You can force it to make an incorrect prediction. So this panda turns into a gibbon, for example, with a very tiny, imperceptible perturbation. Okay? What can you do about that? Well, there are a bunch of things you can do, but one thing is that you can train for robustness. You can train whatever classifier you have, which I've captured in this loss function h, so that it doesn't just do a good job on classifying AJ, but it actually draws a ball of radius epsilon about AJ and makes sure that it does a good job on that entire ball, so that it can tolerate perturbations up to size epsilon, for example. So you can write this down as a min-max optimization problem, where you're trying to minimize over the parameters x of whatever the classifier is, but you're trying to maximize the worst case classification over the entire ball centered at AJ. And we'll get back to problems like this as well. There was a tutorial at NeurIPS 2018. This is still an active area of research by Coulter and Madry on this topic. Distributionally robust learning. This is where it's another perspective on this robustness issue, so that it takes the viewpoint that the training data that you're working with is drawn from some true unknown distribution that I'll call P. So you can think of the M items of training data as being an empirical approximation to P. Ideally, what you want to do in training the classifier is to use the exact P, but you don't know what that is. All you've got to work with is this empirical approximation. So distributionally robust training says, well, okay, I'm going to do the next best thing. I'm going to take a ball of radius epsilon around PM, the empirically observed distribution, and I'm going to solve a min-max problem over that ball of distributions. So you have to decide, how am I going to measure distance between distributions? And for that you use, for example, Wasserstein measures are very popular. Also divergence measures have been proposed as well. So this gives you a min-max optimization problem. For some losses h and for some distance measures, you can write these down as tractable optimization problems. And there's quite a bit of recent work on that. Picking up on this min-max theme, which is shown up in my last few examples, here is a paradigm that crops up surprisingly often in data science. It's a convex-concave problem. So you've got convexity in the x variables and concavity in the y variables. And you want to find the min-max. You want to find a saddle point for this loss function L. That is a point where if you look in the x direction, it looks like a minimum. When you look in the y direction, it looks like a maximum. Okay? But this L has a special form. It's got a general convex g of x in it, okay, which is good for convexity in x. It's got a concave HJ. Well, the HJ stars are actually conjugates of convex functions for technical reasons, but the HJ stars are themselves convex. Because there's a minus in front of them, they become concave, okay? But there's also a term that couples the x and the y. The h and g terms are separate, but this coupling term, y transpose ax, it couples them, but it's linear, okay? It's not a general nonlinear function. And that turns out to capture, the other thing about h is that it's separable. You can break it down into individual components of yj. So this looks like a very specific form, but in fact there's a long list of problems that can be stated in exactly this form. Going back to my first few applications, least squares, L1 regularized least squares, the hinge loss function that's used in SVM, and it's also used in neural nets repeatedly. Tikhonov regularization, total variation regularization, which is used in image processing, logistic regression, DRO with linear models, they all can be stated in this form. Classical linear programming is another example. And so in the second part of the talk, I'm going to come back to algorithms that deal specifically with this problem because they've got such widespread utility. Okay, the last application, reinforcement learning. This again was mentioned in Wotao's talk. So this most usually refers to some sort of Markov decision process. And I think most of you know what that is. In a Markov decision process, you've got a collection of states that your object can be in, and you've got a collection of actions that you can take in response to observing the state. And the purpose of the action is it moves you into a different state according to some probability. And the trick is, how do you choose the appropriate action so that the transitions from one state to the next are optimal in some sense? How do you measure the optimality? After every step, you evaluate a reward function R, which is a function of the state and the action that you're about to take, and you discount that over time using a discount factor gamma. So the goal is to find the best policy for choosing the action at any given state. Okay, and you can write down an objective that you're going to try to maximize, which is this value function. V depends on the policy pi, and the value function at a certain state S is given by the expectation over a certain time horizon of the actions emanating according to that policy. Sequence of actions that come from that policy. Okay, so what we want to do in optimization is to solve a policy maximization, or maximize the value function to find the policy that maximizes the value function. So we can do that. In order to do that, we have to parameterize the policies, and there are a few ways to doing that. One is that you can just define a bunch of finite real values, theta of S and A, which tell you, which parameterize, the chances of taking action A in state S. And you can then define the policy to be this softmax type thing that we've already seen before in other contexts. Another way you can do it is using neural nets. You can actually plug S and A into a neural net and choose the parameters of the neural network to tell you what these theta SA should be, to tell you what the policy should be. And we'll come back to this in the second part of the talk as well. Okay, a comment here about convex and non-convex. For many years, when optimization first became a big thing in machine learning, starting a little bit after, around about 2000 is when I started talking to people in ML, most of the work was focused on convex objectives, and people developed algorithms and did analysis for convex problems. And there are a lot of convex problems, including many of the ones I've just told you about. But really, over the last 8 years or so, non-convex problems have really come to the fore, because neural nets all about non-convexity, robust loss functions more classically involve non-convexity. These low-rank matrix problems, low-rank parameterizations of matrix problems involve non-convexity as well. So non-convexity is known. In optimization, what we typically did when faced with non-convex problems is we kind of threw up our hands and said, well, let's hope we can find a local minimum, and let's be done with that. And in general, for general non-convex problems, that's all you can really guarantee. But it turns out that there's a ton of non-convex problems in machine learning that are actually more tractable than that. The structure that they have and the context that they arrive in makes it quite possible and relatively easy to find global minima. And I'll talk more about that in the second part of the talk. The other thing to notice is that all this work on algorithms for convex problems, it's not wasted, because very often you can just adapt those algorithms to the non-convex case without much trouble. The analysis has to change, of course, but the algorithms themselves often don't change very much. And this is a comment I was just making. There's a whole list of applications where the non-convexity is benign in some sense, where it's actually relatively easy to solve these problems. And I mentioned a few here, including these low-rank matrix problems. Ju Sun has an excellent page where he keeps track of all the literature in this area. He's been doing this for a few years, I think, and he's got a very long list now of problems where non-convexity is proven to be not as bad as people thought. And there are several kinds of reasons for this being benign. One is that you can have problems where there are properties that, yes, there are a lot of local minima, but they all achieve the same objective value. So all local minima are global. So as long as you can find one of the local minima, you're done. Another property that's quite common is that all saddle points are strict saddle points. So saddle points are points where the gradient's flat, but the curvature can either be, the curvature can also be flat, the second derivative, but it could curve upwards like a convex problem in some directions, it could curve downwards in other directions. And so if you can locate those directions where it's curving down, you can escape from those saddle points. So strict saddle points mean that there are directions of negative curvature at every saddle point, so there is always a possibility of escaping. And the other property that makes these problems easy is that very often it's possible to come up with a smart initialization scheme to figure out a good way of choosing the initial x naught. Here's an example, which I'll just go through very quickly, of benign non-convexity that illustrates several of these properties. So in this is the application 3 that we talked about earlier on. This is a symmetric version of that, where the matrix X is the outer product of a skinny matrix Z with itself. Now, you're making these observations that are captured by these operators AJ, okay? Now, if you assume that the AJs have the so-called restricted isometry property, so this is satisfied, for example, if you're taking random linear combinations of the elements of X, you typically get this property being satisfied. Then it turns out that if you write down the non-convex formulation, it's got these beautiful properties. One is that all the local minima are global. The second one is all the stationary points that are not, that are not minima, all stationary points that are not minima, they do have negative curvature direction, so you can get away from them. And the other property is that you've got a very nice way of coming up with a clever initialization. If you just take all those observation operators AJ, multiply them by the YJs, which are the observation, you can show from duality theory that the average of all those YJ times AJs is a good estimate of the solution of the problem. And so you can use that as a starting point. So that's one case in which benign non-convexity is prevalent. Okay, a little bit about neural nets here, and you're going to be hearing all about them in many, many other sessions, so I'll just give you a very quick perspective on this. This is a convolutional neural net where what comes in at the bottom are the raw feature vectors. They undergo a bunch of transformations, and moving between layers, you apply some sort of linear function to the output of one layer to get the inputs to the next layer. Within the layers, something goes on, captured by this element-wise function sigma. Very often that's a ReLU, okay? So you just take the maximum of the input and 0, okay? And the game is that you want to find all of the weights that they're associated with each of the arcs, so that the output nodes are much easier to classify than the input nodes, okay? So that the transformation that you get as a result of the neural network gives you something that's much easier to solve your regression or classification problem or whatever it is you're trying to solve. Okay, now there are many sort of variations on this theme. You can have so-called skip connections in ResNets where you get arcs that sort of skip one layer and go directly to 2 layers above where you are. There are good reasons for doing that. You can have these LSTM nodes, which are useful if you've got data that comes naturally in sequences, like speech or text. You can have convolutions, you can have pooling, local aggregations of inputs, different kinds of structures for the connections between layers. The one I've shown you is a CNN, convolutional neural net, but there are many examples like this. But what they all have in common is that there's an awful lot of parameters all of the weights associated with all of those arcs can be aggregated into parameter vector x, and we can still write it in the same form I've been dealing with here. We can define a loss function, which tells you how good a job the transform feature vector that comes out of the neural net, how good a job that does at matching to the label yj, and that loss function is going to be a function of all the weights in the net that are captured in this vector x. And once again, the goal is to minimize the average loss over all of the observations. But now this is a very large, non-convex, non-linear, and actually non-smooth problem. So, in principle, it's very, very hard to solve. The other thing to notice here is that nowadays in neural nets, and this started to be realized 6 or 7 years ago, the total number of parameters in the net can often vastly exceed the number of items of training. So this is a phenomenon called over-parameterization. And over-parameterized nets tend to do a much better job than sort of tightly parameterized nets. And there's a whole community of people trying to understand why that is from many different perspectives. Okay, a little bit more about neural net training. Usually, in fact, pretty much universally, these are trained with some variant of stochastic gradient, which I'll say a little bit more about in the second part of the talk. Basically, this is gradient descent, but you're not evaluating the entire training set. You're not evaluating the sensitivity of the loss function with respect to all of the training items. You're just taking a batch of training items at each iteration, captured in this subset BK. The choice of the batch size is one of these hyperparameters that need to be tuned in trying to make neural net training work well. The step size AK is another hyperparameter that's a big issue. Another thing to note here is that you can calculate, you can use principles of automatic differentiation. Of course, neural net people invented their own terminology for this. They call it backpropagation, but it's basically classical automatic differentiation. You can use that to calculate these sensitivities of the outputs of H with respect to the XKs. And you can also add momentum terms. We'll talk a little bit more about that later on. The other thing to note here is, as in many other areas of learning, the function that the optimizers have to minimize is this given function over the training data. But what the machine learning people really care about is the predictive performance of the resulting classifier on a test set, okay, which is similar to the training set, hopefully drawn from the same distribution. So that's one of these kind of areas of friction between optimization and ML, at least earlier on, was that when ML people would complain this doesn't do very well on the test set, optimization people would say, but we solved your problem. You gave us a problem of training data, we found the minimum, so don't complain to us. There was something wrong with your formulation. But nowadays people sort of understand that interface a little bit better. Okay, this issue of over-parameterization that I was talking about, when you over-parameterize, it's been observed, well, it's been observed for many years now, that if you train long enough, if you run stochastic gradient for a very long time, you can perfectly fit the training data. You can actually train the neural net to exactly do a correct job of all the classification. And this is what we used to call overfitting, okay? But people realize that even though these things seem to be overfit, they still often generalize well. If you plug in another item of training data that you haven't, test data that you haven't seen before, it will very often do a good job of predicting the label. So, there were two big questions. One is, why aren't we overfitting in this scenario? And the other one is, why is stochastic gradient finding the global minimum? It's finding a zero loss solution, even though this problem is nonlinear, non-convex, non-smooth, okay? And both of these topics, as I said, have been the subject of enormous amount of study in the last few years. One observation that was made a few years ago by Misha Belkin and his colleagues that's really caught on, that sort of goes some way to explaining why neural nets may not be overfitting, is the so-called double descent curve. And many of you would have seen this picture before. In this picture, the x-axis represents the complexity of the model, basically the number of parameters in the model, in the neural net, for example. And the y-axis captures basically the loss function. So the dotted line, the so-called training risk, this is how the optimal value of the loss function changes as I increase the number of parameters in the model. So you can see that the dotted line goes down to 0 and then stays at 0. What this means is that once I make the neural net big enough, I'm able to train to 0 loss. I'm able to get a 0 loss solution. And as I add parameters after that, it stays at 0. Now the solid line is the one that practitioners, machine learning people are more interested in. This is the test risk. Okay, this is the risk that you get, the loss function that you get when you plug in a collection of test data that you didn't train on, but which looks similar to the training data. So in the so-called classical regime, there used to be this sweet spot, this local minimum here of the test risk, which is where the model didn't quite have enough parameters to perfectly fit the training data, but it had enough parameters to get both a reasonable value of the loss for the training data and to also do well on the test data. Okay? If you go beyond that, if you add complexity to the model, the test risk starts going up again because you're sort of overfitting. This is the overfitting region here. But the observation that Belkin made, and others have made related observations to this, is that if you continue to add parameters to the model beyond that point, and you look for a solution that has some sort of low complexity property within that much larger parameter space, you can get the test risk to come down again, okay, beyond that point. And so this is the so-called double descent phenomenon, and it's been proved that this actually happens in various contexts. But you do need to be careful. When you get out into this regime, there are actually multiple solutions. Because there are so many parameters, there are entire manifolds of solutions. And you have to be careful about which one you pick, okay, in order to get this kind of behavior. Okay, and that's basically what I've talked about here. Okay, so here's, one hypothesis for what's going on is that as you add parameters to the model, the manifold of solutions basically grows to fill the parameter space. And so this is kind of an explanation for why optimization works pretty well, is that if you pick a random initial point in that over-parameterized solution space, the chances are you're actually close to the solution manifold because the solution manifold is so pervasive. And so if you just do a bunch of iterations of stochastic gradient, you'll just go to a nearby point on the solution manifold. So that's sort of captured by this picture. If I start at any point in the space, for example, that red point, a few iterations or a few epochs of gradient descent will get me to a point that actually classifies pretty well. Now there's a ton of new work in this kind of general area of over-parameterized zero loss neural net training, and probably you're going to hear a lot at this meeting about some of these. One is this neurotangent kernel. This is for certain kinds of neural nets with a very wide final layer. You can sort of think of them as being a kind of kernel SVM, which I talked about early on, where the kernel is defined by the neural net. There's this phenomenon of neural collapse that if you continue to run the training, stochastic gradient training, even past the point where you've got exact solution, exact fit to the training data, you can get models that generalize better and better, okay? And there's, there's some explanations. There's a paper in PNAS by X.Y. Han and David Donahoe and another collaborator that explained that issue. The choice of loss function is interesting. Classically, people have used that so-called cross-entropy function with the log and the exps in it that I mentioned earlier on. But Misha Belkin showed a couple of years ago that if you just use good old-fashioned linear least squares, that works pretty well too. Different ways of explaining why you're going to a zero-loss solution. I've actually done some work in this space, but it was pioneered by Chizat and Bach in this 2018 paper. Weinan and his collaborators at Princeton have also worked on using mean field analysis and gradient flow to explain this behavior. There are also some very recent papers about this phenomenon of grokking or catapult or slingshot. I've given one example here of a very new paper where they observe that occasionally the loss will spike and then it will go down again, apparently to a better regime, to a better parameter. So the hypothesis is that you're sort of moving between local minima and eventually getting better and better local minima. Okay, but all of these things are, some of them are very empirical, some of them are very theoretical, and they're all ways of sort of trying to understand and explain these phenomena of zero loss training and over-parameterization. So just to summarize, I hope I've shown in this talk with this very sort of high-level overview that optimization provides a lot of powerful frameworks for formulating data science problems. I think the optimization perspective is not running out of things to do in this space. New problems that continue to be thrown at us, new optimization issues where optimization still makes itself useful. It's usually not enough just to use off-the-shelf solvers. You have to sort of dig into the context and the structure to be able to get efficient algorithms, and there are still many unanswered questions. So at this point I'm going to stop. I've got a whole bunch of references here. I'm happy to take questions online or offline, and then we'll just have a short break while I change slide decks. So Karen, do you want to moderate the questions? Okay.
Okay, it's on now.
There we
Right,
are.
if you have questions, if you're on virtual, post your questions in the chat. If you have questions here, just come up and use the mic.
So when you say generalizability improves, even though the loss is zero, is there a regularization term in there?
The loss isn't quite zero. If you're using cross-entropy, it never gets precisely to zero. So you're still, even though each class is kind of the maximum probability, you can still continue to run cross-entropy and get that closer and closer
So
to
that's
1.
been observed even without regularization terms or penalty terms added to that?
Greg, can you answer that? Because he's more of an expert on neural collapse. But I think it happens even without that. There is some analysis of the least squares loss function by Han and Donahoe and their collaborators. They have analyzed cases of that. But
Okay.
yeah.
We can
I think like they have some empirical results in the paper.
Greg, can you use the mic?
Sure. Yeah, so I think there are some empirical results in that paper showing increased generalization accuracy, but I think it's still pretty preliminary. I think there is regularization though, weight decay or batch norm.
Right. So yeah, maybe there is some regularization in there as well. Yeah. Okay, good. Okay, so let me get going again. So this is going to be a little bit similar to the first part of the talk in that I've got a pretty long list of relevant things that I want to get through, and a little bit of information on each one. I'm not going to make you do complicated proofs or anything like that, but I do want to give you an overview of the most kind of interesting, useful techniques from optimization that are used in these formulations that I talked about in the first part of the talk. So gradient algorithms, their extension to Prox gradient, which are cases where you've got non-smooth regularization functions. I'll say a little bit about mirror descent. It's interesting in reinforcement learning. Nesterov's accelerated gradient methods, everyone knows about that. Stochastic gradient, which is probably the most widely used optimization method in ML. Coordinate descent, conditional gradient, also known as Frank-Wolf, primal dual methods. So we'll see how far we get here. I'll start my stopwatch again. Okay, so just recapping a little bit from the first part of the talk. Very often the problems you want to solve have this finite sum form. So little m is the number of items of training data, and you're trying to minimize the average of a bunch of functions fj of x, where each j depends on a different item of j indexes the training data. And the number of variables and the number of terms in the sum can both be very large. So the fj is sometimes convex, as we've noted. There are lots of examples of that. But there are also a lot of problems these days where it's non-convex, low-rank matrices and neural nets. Another thing that happens is very often we add on regularization terms to this function. So we add on lambda, where lambda is some positive scalar, times psi of x, where psi captures something about the properties of x that we're trying to promote. So most typically that's sparsity. For example, we want x to be mostly zeros. But there are other forms of regularization as well. Now, very often the psi is non-smooth, so it introduces non-smoothness into the problem, but in a very structured way. So quite often the f is smooth and the psi is non-smooth, but because the psi is typically a simple problem, we can sort of deal with it pretty easily, as we'll see. And the third form of problem we want to solve is sometimes we want the parameters to belong explicitly to some closed convex set, omega. And so we want to restrict x to be omega. And so there are ways of dealing with that as well. Okay, a little bit more in way of preliminaries. I've talked about convexity already, but I want to talk about optimality for a second. So how do we know that we're at a solution? Well, classically, when f is a smooth function, you just look for a point with a zero gradient. If f is a convex function, that's all you need. You know that if you're at a zero gradient point, you're at a solution. In a non-convex problem, that's not necessarily the case. You might only be at a local solution, or you might only be at a saddle point. That is, there might be ways of escaping from that x star that decrease the function still. And so you can go to a stronger condition, which is second order necessary, which insists that the Hessian is also positive semi-definite. Okay, and this is a pretty good guarantee that you're at a minimizer. It's not an absolute guarantee, but it's pretty good. Now, if you're dealing with a convex function that's not necessarily smooth, you may not be able to differentiate it, but you can still define this concept of a subgradient, and that's a function, a vector g that has this property that basically the true function psi lies above the hyperplane with slope g that goes through the point x, okay? So it's sort of a proxy for the gradient. The subdifferential is the set of all subgradients, and a sufficient condition for x star to be a solution is that 0 is a subgradient at x star, okay? If one of the subgradients of psi at x star is 0, then psi x star is a minimizer of psi. Another preliminary, this is the last one, actually there might be one more after this, but is about smoothness. So if we're prepared to assume things about the smoothness of f, for example, that its gradients have this Lipschitz continuity property, okay? Then we can, that gives us a lot of tools to use in the analysis of optimization methods applied to f. So for example, if we know that L is a Lipschitz constant for the gradients, we can immediately bound f above by this quadratic, okay? And the quadratic on the right-hand side of this expression contains the function evaluated at x, the gradient evaluated at x, and L, okay? And L is the coefficient of the quadratic term. So we can use that bound. It turns out to be super useful in the analysis. In fact, it's going to be useful right now because the first method I'm going to talk about is steepest descent. And this, you know, in a sense, this is the grandfather of all optimization methods that are used in ML at least. And basically the idea here is very, very intuitive. We're trying to minimize f. We generate a sequence of iterates xk. And how do I move from xk to xk plus 1? I evaluate the gradient of f at xk, and I move in the negative gradient direction. So that gives me the direction of steepest descent, exactly as its name suggests. Another way to think of it is that if you actually graph f, you know, using a physical model, you know, of think of a two-dimensional f depends on two variables, and you form this sort of shape where the height of the shape depends on the value of the function. If you were to put a ball on this model at xk and just let it go, it would start rolling in the direction of the negative gradient, okay? So it makes sense. So how can we prove things about the convergence of this method? Well, we can use that quadratic upper bound that I talked about on the last slide. I can just go to this, this model here. I can define x to be xk, z to be xk minus alpha k times the gradient. In fact, if I choose alpha to be 1 over L, where L is a Lipschitz constant, a little bit of work with that quadratic bound, I'm able to show that the function value at xk plus 1 is less than or equal to the function value at xk minus a multiple of the square norm of the gradient. So we're actually able to show that as long as the gradient is not 0, I do get a substantial improvement in the value of f by taking this step, okay? A guaranteed improvement. And I can use that basic inequality to prove a lot of things about how many iterations it takes to get a minimizer of a certain accuracy, okay? So for example, these are the only proofs I'm going to show, by the way, and I'm not going to go through them, so you can relax about that. But I can show that if you apply gradient descent with constant step lengths, 1 over L, to a general smooth f, and if I also know that it's bounded below by f bar, okay, which often you do in ML, you know that the loss function is bounded below by 0, you can show that the minimum gradient that you encounter in the first t iterations, the minimum norm of the gradient, goes down like 1 over square root of t. So you're actually able to make a quantitative prediction of how fast the best gradient that you encounter along the way goes down as a function of the number of iterations, okay? And here's the proof, and it's just based on this thing that I derived on the previous slide here. I just rearranged this thing a little bit, use the fact that the minimum gradient norm that you see is the square root of the minimum squared norm, which is the which is less than the average of the square norms, you know, these are all very basic things, you're able to show that you end up with this bound that I've got up here, okay, 1 over square root of t. Now, if you know something more, if you know that the problem is not a general smooth function, but actually a convex function, you can get a 1 over t bound. The 1 over t bound is on something different here. It's not on the minimum gradient norm. It's on the it's on the difference between the function value at xt and the optimal function value. That goes down like 1 over t as the number of iterations t increases. And again, I work with exactly the same inequality that I had earlier, but I just kind of manipulate it in different ways. This is the entire proof. I'm not hiding anything from you here. I also use this telescoping sums idea, which is a very useful technical device that's used in a lot of optimization analysis. But this is the entire proof here on this slide. I'm just going to show where you end up, and it's this. You're able to show that f of xt minus f star, the optimal f, is L times the initial error in x divided by 2 times t. So it goes down like 1 over t, which is faster than 1 over square root of t. Okay? What if you know additionally that f is strongly convex? It's smooth and also has a curvature that's bounded below by some positive number gamma. Okay, so it's got this bowl shaped. It's not like flat, and whatever. It's always curved. Then you can show an even stronger property. You can show that the non-optimality in the function value at xk plus 1 is less than or equal to a factor strictly less than 1 times the non-optimality in the previous iteration. Okay? So that's what's called linear convergence. People sometimes call it geometric convergence or exponential convergence. Exponential, I don't like the term exponential because it makes it sound super fast, and this is not necessarily super fast. If gamma over L is like 0.00001, this factor is pretty close to 1, so it's not all that fast, but certainly it's typically a lot faster than the sort of sublinear 1 over t or 1 over square root of t rates. And again, we can use the same kind of arguments based on these very elementary inequalities to do with convexity and also to do with the decrease you get from steepest descent. Okay, so you end up with this result. Again, I'm not hiding any of the analysis from you. It's all here on the slide. And you get this quite powerful result. Okay, so we've seen 3 different convergence rates for steepest descent. And we've got progressively stronger expressions for how fast we're converging as we've increased the number of assumptions we make about f. Now we can pose this in a different way. Instead of asking how does the condition go down as a function of number of iterations, I can ask how many iterations does it take before I'm guaranteed to get that condition below some threshold epsilon. Okay, so tell me as a function of epsilon how many iterations I need, for example, to get the gradient below epsilon. Okay, and basically that's just an exercise in turning around the 1 over t into an expression in epsilon. I just have to say, how long does it take before 1 over square root of t drops below epsilon? The answer is clearly t is greater than 1 over epsilon squared. Okay, so that's just an exercise in taking reciprocals. Similarly for 1 over t, for the case where you're decreasing exponentially or geometrically at a rate of 1 minus gamma over L, how big does t need to be to get that below, to get 1 minus gamma L to the t below epsilon? The answer is it needs to be log epsilon over log of 1 minus gamma over L. Okay? Now, if gamma over L is a small number, you can approximate log of 1 minus gamma over L as minus gamma over L. And so essentially this tells you that the number of iterations you need in that case is proportional to the log of epsilon times L over gamma. And you can think of L over gamma as being a condition number. If this were a quadratic function, L would be the maximum eigenvalue of the Hessian, and gamma would be the minimum eigenvalue. So it would be a classical condition number. Okay? So it's proportional to that. So conditioning of the problem still plays a very important role here. Okay, here's my last technical aside, because I'm about to start talking about non-smooth functions that are convex and potentially infinite valued. So this function h that I'm talking about here, it can take infinite values for some values of the argument. So I can take h and I can define this thing called a Moreau envelope. And it depends on h, it also depends on some scalar parameter or positive parameter lambda. And it's a mapping from X to real numbers, and it's defined by this infimum problem. Okay, infimum over U of H of U plus 1 over 2 gamma times U minus X squared. All right? The value of U that achieves that infimum is called the prox of X, the prox of lambda H of X. Okay? So what is this intuitively? Basically, you can think of the Moreau envelope, M of lambda and H, as being a smooth version of H. Even if H has infinite values for some values of its argument, the M, the Moreau envelope, always has finite values for all values of X. Moreover, it's always differentiable. I can write down the derivative explicitly here. It's not non-smooth anymore. And it has minimizers in the same place as H itself. And so it's a lot easier to work with than H. Okay, so the problem is that you have to, in order to evaluate the Moreau envelope, you have to be able to solve this prox problem. And for general H, that's hard, but for H's with specific structure, like with a separable structure, that's relatively easy to do. Okay? So this is going to show up in some of our analysis. In fact, right now. Okay? Because now I'm going to talk about minimizing an objective, phi, which is the sum of a smooth function, f, plus lambda, positive lambda, times a convex but non-smooth function, psi. All right? So how do I do that? I can't do steepest descent anymore because I can't differentiate psi. So I can't just write down the steepest descent formula. But what I can do is take steepest descent steps in the f, and then I can use this prox operator to take account of the psi term. And this is what Wotow referred to as IST, iterative shrinking and thresholding. Sometimes it's called a forward-backward method. But basically it separates out, dealing with gradients in the f with dealing explicitly with the psi at every iteration and going back and forth between those two things. So this kind of method has very similar properties to just steepest descent on the f alone, okay, because you really are accounting explicitly for the psi in this formula. Another way of writing down that prox operator is you can unroll the definition of prox from the previous slide, and you can just say that the new iterate xk plus 1 is the argmin of a linear term plus a sort of a damping term, which penalizes how far you move away from the previous iterate, plus the non-smooth term, which you introduce explicitly. And typically, for the versions of psi that you're interested in ML, this is a pretty easy problem to solve. And the sorts of convergence theory you get are, if f is, for example, convex, you end up with a kind of a 1 over t convergence rate, just like you did in the case of smooth f. So it tends to have similar properties to the corresponding smooth case. Now, you can use this whole prox idea to account for constraint optimization. So if the problem I want to solve is minimize f over x minimize f of x over x belonging to some closed convex set omega, I can write this equivalently as minimizing f plus an indicator function of omega. So this indicator function is defined to have value 0 if x belongs to omega and infinity otherwise. So it's a very nasty function, right? It jumps from being 0 to infinite instantly. This is certainly not differentiable, okay? But we can use this prox idea, we can use Moreau envelopes to smooth out that indicator function. And if we write down the algorithm I've just described here on this slide, if I write this down and set the psi to be the indicator function for omega, what I end up with is the classical gradient projection method. And what gradient projection does, is given in this last formula here, is that it takes a negative gradient step away from xk, and then it projects that back onto the set omega. Okay, finds the nearest point in omega to that steepest descent point. Okay, very classical method, gradient projection. So mirror descent. So mirror descent, it's a very popular technique in ML, and it works best. The best application for it is the case where omega is a so-called probability simplex. So this is a very special set. It's a set of x's in Rn that are all non-negative, but they sum up to 1 as well. So this is a very nice set for capturing distributions, right? Distributions of probabilities over n numbers. Because by definition, probabilities have to sum to 1, okay, or integrate to 1 or whatever. So you can solve, if you're trying to minimize f over this set, you can solve it using gradient projection, which I've already defined on this slide. That's perfectly fine. But mirror descent is another popular alternative, and you can almost think of it as a generalization of the gradient projection idea. So 1.5 slides on how we define mirror descent. We start off with a generating function h, which is a strongly convex function that's defined on the set set omega that I've just defined here. But in fact, you can do this for any convex closed set omega. It's strongly convex, not necessarily with respect to the 2 norm. You can use some other norm if you like, a 1 norm, for example. You can then take h and define the so-called Bregman divergence, and that's best illustrated by this graph here. The Bregman divergence is the gap between h itself, which is the curved line, and this linearized approximation to h, okay? So if I linearize h at a particular point z, and then I look at some other point and look at the gap between h and the linearized approximation, this gives me the so-called Bregman divergence. And you can think of it as a measure of distance, just like the 2 norm is a measure of distance. And so now, instead of doing gradient projection, you use the Bregman divergence as a measure of distance, and you get the mirror descent method. So in fact, if I were to take this last formula on this slide and replace the dh by just z minus xk 2 norm squared, I would recover exactly the gradient projection method of the previous slide. But by generalizing the measure, I get this so-called mirror descent. Now, if I apply mirror descent to this probability simplex, this very specific set that I told you a moment ago, this is the formula that I get for updating xk to get xk plus 1. I basically take minus alpha k times the gradient, I look at each component of that vector, I take exponents of each component, I form these ratios, and basically it gives me a bunch of scaling factors that I apply to the components of xk to give me the components of xk plus 1. You can see this has got nice properties. It makes sure that if you start with an xk that's all positive numbers, after the update it's still going to be all positive numbers. And you can show that they also sum to 1 and so on. So it's got all the properties that we need to stay in the simplex. So I mentioned reinforcement learning or Markov decision processes in the first part of the talk. Here's how you can apply mirror descent to finding optimal policies in this area. So here's a reminder of the function that we're trying to maximize, this discounted reward function summed up over all the time periods, and it's defined for each state and action. So if you apply, now the actions that we can take, they're all taken with a certain probability. So really we've got to minimize over or maximize over the probability simplex. So we can use this mirror descent idea, and our update formula for the policy looks like this. In fact, it looks a lot like what I had on this slide. And so instead of the gradient here, we're using the so-called Q function. So the Q function is so-called a state action function. So it's the value of this V phi, but starting from a given state and action and running out into the future, applying this policy as you go. Okay. So that plays the role of the negative gradient, or the gradient in this case. So this is how you use mirror descent in reinforcement learning. Now there's a little twist here, because this function that we're maximizing in reinforcement learning, it's not concave or convex. You know, it's concave is just a negative of a convex, and because we're trying to maximize, we like to maximize concave functions, just like we like to minimize convex functions. Okay, but this is not concave. But it turns out it sort of looks a little bit like a concave function. There's this famous lemma called the performance difference lemma that goes back 20 years now, that sort of shows that you can get a guaranteed improvement and you can converge to the optimal policy by applying this algorithm, because you can get a guaranteed improvement at each iteration. You can narrow the gap between your current policy and the optimal policy by a certain, at least a certain fixed amount at every iteration. So it looks like you're maximizing a concave function. The wrinkle here is that this argument depends on knowing what this Q function is, and you don't know the Q function. All you can do is estimate it at the current policy. Okay, you can't evaluate the Q function exactly, because it would involve simulating out infinitely far in time, which obviously you can't do. But you can use a sampling process to get inaccurate estimates of the Q function, and you can apply something like, this mirror descent formula, and you can get these guarantees. So there are other techniques that are used to find optimal policies. Trust region policy optimization is one. Proximal policy optimization is another that have been proposed in recent years. Let me just say that trust regions, that's something that I've been interested in for a long time. There's a chapter in my book with Nossadal about trust regions. People kind of weren't very interested in this idea for a long time, but it's been very gratifying to find that people in ML have really latched onto this idea of trust regions. They turn out to be quite useful in those contexts, particularly when you're dealing with non-convex functions. Okay, a little bit about Nesterov acceleration. So this is something very nice that you can do to gradient methods to speed them up. You don't need to use higher order derivatives. You can still just stick to using gradients. But the basic idea is this idea of momentum. And that is that to get from xk to xk plus 1, you don't just move in the negative gradient direction, you also keep going a little bit in the same direction that you're already heading in. So that's captured by the second term here, xk minus 1. That's the step that you just took. So your new step is a combination of the previous step with a little contribution from the negative gradient as well. And okay, so intuitively, why should this be a good idea? Well, I had some pictures to explain this, but unfortunately I left them out of this talk. But basically, you can think of this second term as incorporating the entire history of gradients that you've looked at so far, right? Because if you sort of expand this out and go further back in time than iteration k, what you end up with on the right-hand side, the formula for xk plus 1, is a linear combination of all of the gradients that you've seen from x0, x1, x2, all the way up to xk. So in other words, you're able to account for the entire history of the iteration to this point. And that's kind of a richer collection of information than just the latest gradient. So you can at least see why there's a possibility of exploiting that sort of richness to take potentially a better step. Now, Nesterov's method is just a little bit different. This first one is so-called heavy ball method. It's been around since the 70s. In Nesterov's method, you sort of take the momentum step, which is the beta part of the step, before you evaluate the gradient. That's why I've highlighted it in red here. You take the xk plus beta times xk minus 1. You take that step first, you evaluate the gradient at that point, and then you add it in. You add in a contribution from the negative gradient. So with Nesterov's method, you can actually, here's a little bit more specific about how you do that, about how you choose the alpha. You can just choose alpha to be 1 over L again, just like we did in steepest descent. Choosing beta is very complicated. I've given you all the gory details here. You have to solve a little quadratic at every point to get the beta with all the nice properties. But here's what you end up with, is that the function decreases towards its optimal value at a rate of 1 over t squared, okay? And this is for convex f. So that's better than for steepest descent. Steepest descent was 1 over t. This is 1 over t squared. So that's going down faster, okay? The proof is very technical. People have made various attempts over the years to simplify the proof or look at it from different perspectives, but it remains kind of a challenging thing to understand, but you end up with this better rate. Also, there's a variant of Nesterov acceleration that you can use for strongly convex functions f. Now, you'll recall that when we applied steepest descent to strongly convex f, we got convergence in order of L over gamma times log epsilon iterations, okay? If you apply Nesterov acceleration to the strongly convex case, you get a fewer iterations. You only need square root of L over gamma. So if you've got a very ill-conditioned problem where L over gamma is like 10 to the 6 or 10 to the 8, the number of iterations drops from order 10 to the 6 or 10 to the 8 down to order 10 to the 3 or 10 to the 4, which is a pretty big improvement, okay? So, by the way, this momentum idea had actually been around longer. It's exactly the same idea that's used in conjugate gradient. Conjugate gradient for quadratic convex objectives. That had been around since Hestene's work in the 50s. And conjugate gradient is just a momentum method. Of course, extending conjugate gradient to the nonlinear case is difficult, and you can do that easily for Nesterov. So that's one advantage that Nesterov has. Okay, so let's step back a bit. I've talked about methods that make use of full gradients, and it's fair to ask, if you're dealing with ML problems, can you actually calculate full gradients? Well, sometimes you can. If you're dealing with a matrix completion problem, a low rank matrix problem, where these matrices, where the rank is very small, like 2 or 3, and the dimension is, 10,000 or 100,000, then fine, you can get an entire gradient for that. It's not a big deal. And there are some other examples as well. But if you're dealing with training a neural net, and you want to evaluate the gradient of the full loss function, you have to look at all the training data, right? So you have to pass all the training data through the neural net, you have to backpropagate it, you have to get all of the gradients for every item of training data, you have to take the average. That's a heck of a lot of work, okay? So in practice, it really doesn't make sense to do that. So can we get away with just using estimates of the full gradient that are much cheaper to get? And in fact, that's where stochastic gradient comes in, okay? Instead of looking at the full gradient, the average of all the terms in the sum, you just take a sample from that sum. You might just take one term, for example, or you might take a mini batch of terms, maybe 1,000 terms or something like that. And you just take the average over that mini batch, and that gives you an unbiased estimate of the full gradient, okay? Now the drawback of this is that the variance might be very large. The expectation of your gradient estimate might be unbiased, but it might look very different from the true gradient. And the upshot of that is that although each iteration is going to be cheaper, because it's going to be cheap to evaluate that gradient, you might need many more iterations, okay? So there are things you can do to smooth it out. One is to use a bigger mini batch. The bigger you make the mini batch, the closer the estimate's going to be to the gradient. You can reduce the variance that way. Another thing you can do is to average out all the iterates that you've seen so far, because the individual iterates might jag around a whole lot. But if you take a running weighted average of all the iterates, you might get something that behaves much more smoothly. And in fact, some of the analysis of these methods does assume that you're taking a weighted average. Okay, so here's a little bit of the kinds of analytical results you can get for stochastic gradient. And in this book that I told you about at the start with Ben Recht, we sort of consider this general approach where we make assumptions on the sum of the squares of the norms of the individual gradients. We make assumptions about how they depend on the current iterate x and the optimal iterate x star. Now you know that at the optimal iterate x star, the true gradient is 0, okay? So that bound, we assume it's bounded by some function b, or some constant b, or b squared, but it's also bounded by some multiple of x minus x star squared, okay? So depending on the value of b and the value of LG, you can prove different things about the rate of convergence of stochastic gradient. So in general, if f is strongly convex for general b and LG, you can prove that you get a 1 over k or 1 over t type convergence rate. So that's like what you get for strongly convex, that's like what you get for a general convex function f with a full gradient, okay? For SGD, to get the same rate, you need a strongly convex f, okay? If you've only got a general convex f, the convergence rate is 1 over square root of k rather than 1 over k for the full gradient. So that, again, is a little bit worse. Now, in the special case where the b is 0 in this expression, in other words, where the variance of the individual gradients is shrinking to 0 as the iterates converge to x star, then in effect, your gradient estimates are getting more and more accurate as you approach the solution, even though you're only taking a mini batch, okay? And then you can prove that you get a linear convergence rate. You recover this 1 minus delta to the k rate that we would get for strongly convex functions for the full gradient, okay? So you can still get linear convergence for SGD, provided your individual gradients all behave well. Also, we don't have to work with a finite sum here. All of the analysis that you need to get these results, it will generalize to the case where the f of x is an expectation over a random variable with infinite support, a random variable psi which has infinite support. So we're not restricted to just finite sums here. Okay, so I told you earlier that SGD, I used to hate calling it SGD because it's not a descent method. It doesn't actually go down at every iteration. But everyone calls it SGD now, so I've had to give up on that. But it is the method that's used to train neural nets, but there are different variants that people apply to make it work better in practice. And there's one that's kind of been sensationally successful, and it's this atom variant that was proposed in a 2015 paper, which has 120,000 citations now. And basically the idea is that you scale the components of the descent direction by sort of keeping a running tally of what's happening to the gradient in each individual component. Okay, in a way, it's sort of a way of automatically scaling, appropriately scaling the elements of the gradient. It's related to an old idea in optimization, which is a Newton-type method where you just use a diagonal approximation to the Hessian. This idea has been around for a long time. The diagonal of the Hessian sort of gives you information about the scaling of each of the components of X. And by using the inverse of those and applying that to the components of the gradient, you can get a method that behaves faster. So atom is very much that kind of idea. And really, these days, people seem to use atom universally for in applications like neural net training. Another thing you can do to speed up stochastic gradient is to sort of hybridize it with full gradient methods. And these ideas started to appear about 10 years ago, these methods SAG and SAGA and SVRG. And their basic idea is that well, in the case of SAG and SAGA, they sort of maintain an approximation to the full gradient over the full set of M training examples. But what happens at each individual iteration is that they refresh part of that estimate. Okay, they take some of the GKs and replace them with the latest value of the gradient for that J, okay? And they do that in slightly different ways in SAG and SAGA. SVRG is a little bit more explicit. SVRG, it just takes SGD steps, but every so often it evaluates a full gradient and then just repeat, and then sort of updates it with a bunch of SGD steps and then evaluates a full gradient again. So they're both, you can think of them both as being sort of hybrids of full gradient and stochastic gradient. Now you might think, well, you know, SAG is not going to work because I have to store estimates GJ of the gradient of every individual FJ. And you think, well, that's, you know, each of those vectors is length n, that's going to be a horrific amount of storage. But in fact, for a lot of special cases, that's not the case. So if each Fj has the form of a scalar function of Aj transpose X, where Aj is the feature vector, then the gradient of that Fj has the form of Aj, the vector, times a scalar, the scalar being phi prime, okay? So in order to keep track of the gradient values, all you really need to store is that scalar phi prime. The AJs you have to store anyway, right? That's the data of the problem. So you just need to keep track of the phi prime. So it is actually possible to implement SAG and SAGA in very efficient ways. And sometimes on some problems, they seem to improve performance. Okay, a little bit about coordinate descent. This is another thing that turns out to be useful in a bunch of applications. The idea here is that you don't want to update all the components of X at once. You want to just evaluate a part of the gradient and use that part of the gradient to evaluate just the corresponding components of XK. Now this is premised on the fact that it's cheaper to evaluate a part of the gradient or an individual element of the gradient than it is to evaluate the full gradient. And sometimes that's true, okay? There are lots of interesting examples where it does cost you much less to evaluate a single component than the whole thing. So coordinate descent, it's been around in practice for many, many years. It was really only about 12 years ago that people started to develop theory, convergence theory for it. And there are also different variants of coordinate descent. There can be the cyclic version where you just cycle around the components of X, going from 1 to n and then back to 1 again. There's the randomized version where you just, at every iteration, you just pick a random component of X and update that. And there's the randomized permutations version where you shuffle the components of X, you work through them in shuffled order, and then you reshuffle and repeat, okay? Now, all of those have different convergence analyses, but the bottom line is that sometimes you can converge faster than full gradient descent. If you've got a situation where the individual components of H are easy to evaluate, if you're prepared to make certain assumptions about the nature of the gradients, the Lipschitz constants for the gradients, you can actually get faster performance for these component-wise versions than you can for full gradient, okay? And I've got a few details about this here. The first one is from Nesterov's 2012 paper, where he's actually able to show that the bottom line is that you get this 1 over k convergence, which is the same sort of convergence rate you get for steepest descent, but the difference is the numerator has an L max in it rather than an L. So remember, L is the Lipschitz constant for the full gradient. What L max is it's the max of the Lipschitz constants for the individual components of the gradient, okay? And that can be a lot smaller. It can be smaller by a factor of up to n, okay? So you can potentially get a much smaller constant in the convergence expression for the function. Okay. There are a lot of extensions to the coordinate descent idea. You can extend it beyond just taking a single component to blocks of components. This actually is an old idea in support vector machines. There's one of the very popular algorithms in SVM was due to Platt from the 90s. And he basically did coordinate descent where he chose 2 components to update and made them move in opposite directions because you had to satisfy a single linear constraint, y transpose alpha equals 0. So if you chose 1 component of alpha to change, it was going to mess you up with respect to that constraint. So you just picked another component, and so the 2 of them moving together were able to maintain feasibility. Okay, so that idea had been around much earlier in SVM. You can also do Nesterov type acceleration. This was shown by Lee and Sidford, showed how to do this efficiently in 2013. You can adapt it to the case where you add on a regularization term. And also a bunch of us did work dating right back to Bertzakis and Tsitsiklis in the 80s, more recently by Ji Lu and myself back about 10 years ago, where we did things on parallel asynchronous versions of coordinate descent, where you could have different cores of a computer working with different parts of the x vector at the same time and not trying to coordinate. And you could still show that you got good parallel performance and good convergence. Okay, the Frank-Wolf method, conditional gradient. This is where you're trying to minimize a convex function over a closed convex bounded set. So there are interesting problems like this. For example, when omega is the probability simplex, that's closed convex bounded set. And the idea is very, very simple. You just linearize f around the current iterate xk. You just form a linear approximation to f, and you minimize that linear approximation over omega, the original set omega. And there are situations, for example, a probability simplex, where that minimization is trivial. You can do it in closed form using very, very little computation. You just need to find the max of a vector, okay? And then having found that solution, you take a small step from the current iterate xk in that direction that you just calculated with a certain prescribed step length. So this is the original method. It dates to the 1950s by Frank and Wolf, obviously as the popular name suggests. Frank was, it was sort of reinvented by Martin Yagi, or not reinvented because he knew about the original algorithm, but in a 2013 paper he showed that it was very useful in various ML contexts. And then Frank, who was, I think, a master's student when this paper was written in the 50s, was invited back to a workshop, I think at an ICML or NeurIPS meeting, and she was, I think she was now in her 80s, and she was very pleased to find that this method had turned out to be so useful. A little bit about augmented Lagrangian. Again, this is a method that's been known since the 70s. It's due to Hestenes and Rockefeller. Developed and popularized by Bertzakis in the 80s and beyond. And it's sort of waxed and waned in popularity and optimization over the years. There was a code called Lancelot that was written around 1990 by Congoul and Twant that was based on augmented Lagrangian. That was somewhat superseded by, about 10 years later, by a generation of interior point solvers. And so augmented Lagrangian was kind of shunted to the side, but then it was discovered to be very useful in ML context. So it's over the last 10 years, it's undergone a sort of revival in the ML community. So the idea is, this is just for the case of equality, linear equality constraints. It generalizes beyond this to inequality constraints and nonlinear constraints. But the idea is you write down a Lagrangian function, which is a very classical object in constraint optimization, which is a combination of the objective and a linear combination of the constraints. You can write down optimality conditions in terms of so-called Lagrange multipliers, the lambdas, which are the coefficient vector for the constraints. And you can write down an algorithm based on the Lagrangian. You take the Lagrangian function and you add on a quadratic penalization term that penalizes violation of the constraints. So this last term here, the ax minus b squared, obviously it's 0 if ax equals b, if the constraints are satisfied. If they're not satisfied, you pay a price, okay? And the algorithm is very simple. It just goes back and forth between minimizing this augmented Lagrangian function for a fixed value of lambda and a fixed value of the penalty parameter rho. So that's how it updates the x. And then it applies this formula to update the lambda. If you've got additional constraints on x, that's totally fine. You can just incorporate them into the update formula for x. You can show that you can derive this method as being a proximal point method on the dual. Okay, if you write down the dual of this problem and write down a so-called proximal point method where you penalize moves in the dual by a least squares penalty from the previous iterate, it ends up being exactly equivalent to what I've described here. Now, one reason augmented Lagrangians become so popular is that it's the basis of this so-called ADMM approach, alternating direction method of multipliers. And this is for problems that have exactly the form that I showed on the previous few slides, but you can break down the objective into two components, a component involving x and a component involving z, each of which may also be constrained to their own feasible set, omega x and omega z, okay? So if you write down the augmented Lagrangian for that problem, instead of minimizing over x and z jointly to get the update, you can minimize separately over x and then over z. And it could be that doing those separate minimizations is much easier, much faster than doing the joint minimization, okay? So there was this review paper of Boyd and Eckstein and others in 2011 that has a gazillion citations as well. It was written at exactly the right time when this idea was turning out to be very useful in ML. But it goes back to John Eckstein's thesis around 1990 in his work with when Bertsakis was his advisor. Now you might look at this and say, well, this is kind of a clever thing to do, but if you could optimize over x and z, surely you would do better than this. Or maybe instead of just optimizing once over x and once over z and then updating lambda, maybe you should cycle around updating x and z until you've kind of converged and then go on and update lambda. Turns out that's not a good idea. And there is some work by Eckstein from, I don't know, 6 or 7 years ago where he shows that it's actually better to do it this way. And he has arguments that explain why that's the case. Okay, a little bit, we're getting towards the end now, a little bit about that problem that I flashed up at the end of the first talk, and that is this min-max problem where the coupling between the min and the max variables is this bilinear term, y transpose ax, okay? So what are the algorithms you can use to attack that? Well, the most basic one is so-called gradient descent ascent. And what it does is essentially it fixes the y and then takes a derivative of this thing with respect to the x, and that's just going to be a transpose y plus whatever you get from the g. And it takes a prox gradient update in the x for a fixed y, okay? Exactly like the prox linear method I showed earlier in this part of the talk. And then it does the same thing for the y. It fixes the x at its latest value. It finds the gradient of this objective with respect to y, which is just going to be ax, and it takes a prox update in that component. So it just goes back and forth in taking prox gradient steps in the x and the y. A very intuitive thing to do. So that's called gradient descent ascent. It turns out in 2011, Chambol and Pock came up with a thing that looks very similar, but turns out to be much nicer. And it looks almost like prox gradient descent, but it has this extra extrapolation term in the middle. So instead of taking a transpose y as the gradient contribution, it takes 2yk minus the previous y, k minus 1. And for various reasons, that turns out to be a better idea. It's related to, connected to Douglas-Ratchford splitting, extrapolated gradient ideas, ADMM. It's got a lot of interesting connections. There's also this nice paper from 2020 with lots of pictures in it, which shows why using this kind of extrapolation can boost the convergence properties of the method, but it's sort of too complicated to cover right now. But this is kind of the granddaddy of methods for these min-max problems, PDHG. There are many, many modifications and enhancements that can be applied to the basic PDHG idea. You can do something like you don't update all the components of the Y. You might use coordinate descent to just update some of them. There are variance reduction ideas where you use coordinate updates, but you use some kind of smoothing to sort of smooth out the large, variations in that. You can do dual averaging. You can average over all the Y iterates instead of taking just the last one. You can use importance sampling. You can use iterate averaging, all kinds of different ideas. We've done some recent work in this space with two methods that have appeared recently in, well, the upcoming Europes and last year's ICML that incorporate all of these different ideas into PDHG and can improve the convergence properties accordingly. Lastly, a little bit about variational inequality. So Wotow mentioned GANs in his talk, and many of you know about these things. These are like two dueling neural nets, and the idea has been very successful in several applications. One way to formulate these as optimization problems involves writing them down as a so-called variational inequality. So here you're not trying to necessarily optimize anything. You've got a mapping F and a set Z, and you're trying to find a point Z star with this property, that Z star, when you evaluate F at Z star, it makes a positive inner product with Z minus Z star for all Z belonging to the set, okay? So you can think of this as being the optimality conditions for minimizing an F over the set Z. That's one thing you can do, but you can also use it to formulate min-max problems, like the problems I've described on the previous few slides. Oh, I've gone way back here. Let me zoom ahead. Okay, so you can write down optimality conditions for min-max problems as being, by defining the function big F as being the gradient of little f with respect to x and the negative gradient of little f with respect to y. You can also use this to formulate problems in game theory when you're looking for Nash equilibriums in game theory. And this is where the GANs come in, because the GANs are basically playing games against each other. You can write down optimality conditions as a VI. So once again, the sorts of algorithms that you use for VI, they look a lot like Prox gradient methods, except instead of the gradient of an objective f, you actually use the mapping big F. So there are so-called extra gradient approaches dating back to the 70s, and there's Popov's algorithm, which looks quite similar from 1980, that have these forms. And again, I'm not going to talk about the properties of these, but you can prove things about convergence rates for these kinds of methods. So I just want to point out, I'm coming to the end now, I just want to point out that there are many things I didn't discuss here. I didn't talk about Newton or quasi-Newton methods. They've kind of been on the fringes of ML applications for a long, long time. People always feel we're right on the verge of making them work well for, contexts like deep neural nets, but they haven't yet made it into practice as far as I know. A lot of machine learning you can reduce to just systems of linear equations, sometimes overdetermined, sometimes underdetermined, and there are these methods called Kashmar's methods for solving those, which I didn't talk about. There are lots of cool applications in image and video processing. They're formulatable as optimization problems with various kinds of regularizers. I didn't get to talk about those. I didn't talk about graphs very much, except a little bit in the first part of the talk. I've talked predominantly about continuous optimization issues. There are also lots of opportunities for integer and combinatorial optimization. As you know, those problems are much harder to solve, and so it's harder to make them practical, but certainly people are attempting to use those in an ML context. I didn't say much about parallel methods, although they're very important in practice, and there has been a lot of work on those. I didn't talk about online learning. I didn't say all that much about non-convex formulations. But that's it. I've finished on time, which is amazing. And there's a whole bunch of references here. So I'm happy to share the slides. I guess they'll go up on the meeting site. So if you want to dig more into any of these issues, there's plenty of stuff for you to refer to. So thanks very much. I'm happy to answer questions.
Oh, the music's starting. All right, thanks so much, Steve. That was an amazing tour of optimization methods, and clearly such a long history and also many exciting open challenges. So we are almost up on time, but if there are any questions, just come up here to the mic, or if you're online, stick something in the chat.
Yeah.
And if you can just get very close to the mic, they said.
Hey, how are you? My name is Jordan, and I just have a quick question about the presentation. I really want to ask and see, will the presentation be able for us to like view and read at our own pace?
Absolutely, yeah.
Oh, yes, sir.
Yeah,
That's
yeah.
what I want to know. Like,
Yeah, I think the slides are going to be posted, and the recording is going to be posted on the meeting site within a month. That's what
Okay.
Leo told us in the opening session. But if you email me, I'm happy to send you the slides.
okay, yes, sir. Yeah, I would love that. It's actually I
Great.
can take my time and understand it.
Absolutely, yeah. Thanks.
And you should buy a copy of the book.
Oh, yeah, yeah. I
books.
forgot to say that, yeah.
But otherwise, again, thank you so much, Steve. This
Sure.
has been wonderful.
Great, thank you.